Hello guys, welcome to Algorithms Made Easy. Today we will be discussing the question shortest subarray with sum at least k. In this question we are given an integer array and an integer k, and we need to return the length of the shortest subarray of nums with a sum of at least equal to k. If there is no such subarray, we need to return -1. We are given certain examples with that. With example 1, wherein the array only has one value and k is equals to 1, so output is 1. In the second example, we are given two values in the array 1 and 2 and k is equals to 4, as we cannot make the sum at least 4 even by using both the values, we'll return -1. Lastly, we have the third example in which there are three values and the sum should be 3. We can make the sum with at least 3 by using all the three values, so we return output as 3. Now let's discuss how we can solve this problem. At first glance, we can come up with an n-square solution, which is a brute force solution in which what we do is we iterate over the nums array, and inside that we again iterate over all the values after that index, so to find a continuous subarray which will give us the sum of at least k. Now that becomes our n-square solution. So that's the first part. As we know by the constraints that this solution won't hold. So let's dive deep into the problem and see how we can solve this particular problem by optimizing our n-square approach. So let's assume that this is the array that is given to us and the sum that we need to find is at least 37. Let's first see what would be the answer of this particular problem. So if we take the sum of these three values, it comes out to be 39, which is at least 37. So the length now becomes minimum of 3. Now we see that there lies two values whose sum is 43, and that is even better result than what we have found up till now. So the length becomes 2 and the answer is 2 in this particular case. So now you must all be thinking that can we solve this particular problem using 2 pointers? That was my first guess when I looked into this particular problem. So to clear out all your dilemmas and to help you not waste your time using this particular approach, I would say that no, we cannot use 2 pointers in this particular problem. And now we will discuss why we cannot use that. So I told about 2 pointers, and some of you won't know what 2 pointer is, and we will discuss that. Rest of you can jump to the part where we discuss the problem after this 2 pointer, or you can just stay here and refresh the 2 pointer. So now let's look into what the 2 pointer approach is. As the name suggests, we would have 2 pointers pointing at the start of the index. Let's say these are left or right. Now when the sum is less than the required answer, we need to increase our window so that the sum increases to the particular value that we are seeking, and we keep on incrementing that until we reach that particular point. Now that we have reached the point, the sum is now 49, which is greater than 37. What we need to do? We need to decrement the window. So the next step is, when the sum is greater, we need to decrement the window. At each point we are finding out the minimum window size. We decrement the window until the sum is less than the required sum that we are trying to find, and that's how we find out the answer. Now what is the problem? Why we cannot apply 2 pointer in this particular question? Let's change some of the values in line with the constraints given to us and then see if the logic still holds. So we have changed the value as -22 now, and now when we are increasing the size of the window, which is what we do when the sum is less than the required answer, the sum got even less than what we had previously, which implies that how would we know if by increasing the window size we will be getting a bigger sum or a less sum? So a 2 pointer approach is usually good in an array which has all positive value, and since there are negative values in this particular array, we cannot apply 2 pointers in this problem. So now let's take a realistic example in which there are already negative values so that we can come up with a solution to it. as we discussed our n squared solution, so for every index we are iterating over all the indexes after that particular index, which means that for first index we won't be finding an answer starting from 0th index. For fourth index we won't be finding out answer from 0, 1, 2, 3. We will be directly starting from the index itself. Now the next part, if a window starts from its own and end on the same index, the answer is nothing but the value present at that index. So we'll have all those values in this particular grid. Now this is not the actual solution that we will be using. It's just the approach that we will be discussing. Now what does 2, 4 means? This particular cell represents sum of all the values starting from index 2 to 4 where both the indexes are included. I'll repeat that. 2, 4 in this particular grid represents that we are taking into consideration all the values starting from index 2 and ending at index 4, including both the values at that particular index. So both the values are inclusive in this case. So let's, for an instance, we have all the values starting from 0th index to that particular index. That is very easy to find. Now, how can we find out the value of this cell 2, 4? Now let's say we take a variable which is s of I, which is sum from 0 to ith index. So the sum at 0, 2 will become s2, which represents the sum starting from 0th index to 2nd index. If we see that the value at cell 2, 4 is nothing but s4 minus s1. Now why s1? Because we need the value starting from index 2. We need the value at index 2 as well. So we will remove all the sum that we have found till the index before 2, which is index 1. So s4 minus s1 will give the answer to the cell 2, 4. If we find out the answer, it comes out to be 16. If we add the values 13, 15 and minus 12, we'll still get the same answer. Now we have put that value into the cell. But what we have learned over here? We have learned that we can find out the sum from any index to any other index if we have the value or the sum starting from 0th index to that particular index. If we have all those values, we will be able to find out the sum from any index to any other index. Now, let's take this learning and move forward with how we can use this particular values. So we have removed all the unnecessary details. We'll just have the numeric array given to us. We have the index and we have s of I, which is nothing but sum from 0 to that particular index. Now sum of values between 2 and 4 was s4 minus s1. We discussed that. Why s1? Because we need to remove all the sum before index 2, and that is represented by the value s of 1. So effectively what we are trying to find, that if 2, 4 means a window starting from 2 ending at 4 is greater than equals to the target sum or not. So can we write if s of j minus s of I is greater than target, where j is greater than I? That is the generalization of a very specific window. We are saying that if there is a window starting from ith index and ending at jth index, will it give a sum which is greater than the target that we are trying to find out here? So can we write this equation like this as well, which is if we subtract the target sum from s of j, it will be less than or equals to s of I. So what we are effectively trying to find out at every index is, for every index j, we need to find an index I whose sum is less than or equal to sum till j minus the target sum, which is effectively represented by this particular equation. So s of I should be less than or equals to s of j minus target, and we need to find that at each index. So let's take an example. At index 3, what we are trying to find? Index 3, we are trying to find if s of 3 minus s of I is greater than or equals to 37. Now we need to find an index whose sum is less than s of 3 minus 37. So we put the value of s of 3, which is 27. We find out that we need to find an index where the sum is less than equals to minus 10, and it should be an index which is less than the current index, which is 3. So can we do that? Do you see any value which is less than or equals to minus 10 before index 3? We do not. That means the window cannot end at 3 starting from any index before that, which will give us the target sum. Now, moving forward, let's take another example. In this case, we are at index 5. We put all the values, and now we need to find out an index which is less than or equals to minus 1. We need to find an index where sum is less than or equals to minus 1. Do you see any index before index 5 where the sum was less than or equals to minus 1? Yes, we do see that it is index 1. So between the two indexes, if we calculate the sum adding 13, 15, minus 12 and 21, we will get a sum which is greater than 37 or equals to 37. So the window size in this case is 5 minus 1, which is 4. So 4 is the answer. Now let's take another example. Here we have some of the values. We have an array of size 5. The target is 89. So what we were doing, let's dry run what we were doing step by step. Previously we had all the sum with us. Now we'll try to fill that, and then we'll try to find out. We have this equation with us where we need to find out index I for every index j, where sum of I is less than or equals to sum of j minus target. So when we are at index 0, we do not have any sum with us. We write down if the sum of I is less than or equals to minus 28 minus 89, which is less than or equals to minus 117. There is no index before 0. We move ahead. We move to second index. The sum at index 1 is 53. We put that into equation. We need to find out an index I where the sum is less than or equals to minus 36. We do not find it. We move ahead. Then we put the values for index 2. We need to find out index I less than or equals to minus 56. We do not find it. We move ahead. Then we come at index 3, put the values. We need to find index which is less than or equals to minus 28. We find that index. It is index 0. So we get an answer which is the current index minus the index of the sum less than j minus target, which is 3 minus 0 is 3. So that becomes the window size. We'll keep that answer with us and move to the next index. Over there we'll find out if we can find an index for that as well. We need to find out the sum which is less than minus 57. We do not find that, so we complete our iteration. We find out the answer is 3. So that is what becomes the result that we need to find. If you add the 3 values, it will give us the target as 89. So this is the right answer. So what we were doing, we were storing the previous sum and the index. There were 2 values that we need to take care of, that we were using continuously. We are using the previous sum, we are using the index. So we need to store these 2 values. And as you can see, there has to be a relationship between those 2. So now the second step that we were doing, we need to find out the sum which is less than or equal to some value. As we are iterating starting from 0th index, the sum present to us will always be of index less than the current index. So we need to just find out if there exists a sum which is less than or equal to the sum that we have got from the equation. So how should we do it? How we can solve this particular problem in the manner that we have discussed? The first question that you should ask will be how we are storing the previous sum and the index. And the second question that you need to ask, which is related to the first part, is whatever way you are storing the previous sum in the index, how efficiently will we able to find out if the sum is less than or equal to some value. So combining these two steps, we need to find out a data structure which stores the value in a relationship and then also provide us a method wherein we can efficiently find out if certain sum less than or equal to the value that we are finding exists or not. So like always, try that with yourself. Comment down what was your first guess. And now for us, it's time to code this particular approach. So let's define some variables which we will be needing in the coding. So we have defined a length, we have defined the intermittent sum that we need to take care of, and we have defined the result, which will initially be the max value. We know that if we do not find any value, the result will still be max, so we'll return -1, otherwise we will return the result. Now the part which I asked you to guess about, what should we use in order to store the intermittent sum? So the answer was tree map. We will use a tree map because it provides us two functionalities that we need in this particular problem. It stores the value into a key value pair. And second, it gives out certain functions or methods which enables us to find out if there exists some key less than equals to or greater than or equals to the key that we are trying to find, and that too in log n complexity, which means effectively tree map stores all the keys in a binary tree fashion so that the searching becomes easy and it gives out the result to us in log n complexity. So let's define a tree map. So as you can see, the key is of type long and the value is of type integer, because in the key we'll be storing the sum so that we can easily find out whether the sum that we are finding is less than or greater than the sum. The integer will store the index value. We have taken long because the range of the values in nums can go from -10 raised to power 5 to 10 raised to power 5. So all the values in a very big array will cross the limit the integer can hold, so we'll need a long value. We discussed that we need to iterate over the array. Now for every iteration, we need to find out the sum till this particular index. Before that, we can put in an extra condition wherein we check if the value at this particular index is greater than or equals to the target that we are trying to find. If that's the case, we'll directly return 1 because that is the smallest window. Now we need to increment the sum with the value present at this particular index. The variable sum is holding the sum starting from index 0 to this particular index. Now there can be a scenario wherein the start of the window is from 0th index. So in that case, we'll check if the sum is greater than or equals to the target, and then we update the result. The result will nothing but the minimum of the current value and I plus 1, because the first index is 0, current index is I, so the size of the window is I plus 1. Now we need to find out an index prior to this index I wherein the sum is less than the current sum minus the target. So let's take that in a variable and let's call that variable as remaining sum. Now we need to find out if there exists a value in map which is less than or equals to the remaining sum. Now tree map provides us certain functions or methods which will do that for us in a very optimized time. The method that we are talking about over here is called floor entry, which gives us an entry object which has the key and the value which is less than the remaining sum that we are trying to find. Let's define that. Now if there exists any value which is less than or equals to the remaining sum, then the entry variable will have it, otherwise this variable will be null. So we need to find out the size of the window if this entry object is not null. Now there can exist multiple values in the map which are less than the remaining sum, and we need to take care of all those values. because in all those values we need to find out the value which gives us the minimum window. So we'll iterate through all those values using a while loop. We'll iterate till the entry is not null. Let's find the index which is present in this entry, which is nothing but the value present in this object. So we'll take that in a variable index. We will now find out what is the window size starting from this particular index that we have defined or find out, and with the index I. So we'll update the result similar to what we did before. I being the higher index, we'll do I minus index. Now we need to find out the next entry object which is less than this particular key. We'll update the entry object again by using the same function, floor entry. The key of this object can be get by get key, and we find a smaller value than that, as floor entry gives out any value which is less than or equals to. So if we do not do -1, we'll continuously find out the same key. As we are finding out the answer from this map and reusing them, we need to put some values into this map at each index. So we'll put the sum that we get over here along with its index into the map. Now here the coding is done, but there is one line of logic which is missing, which would effectively decrease the time complexity of this problem. Now let's first discuss that and then we can write that down. If we find out any index, this particular index, and we have a combination now with index and I. So if a window starts from this particular index, and as we are going forward with the I, and in the next iteration where I is greater and we find out again the same index, will the window be shorter or larger? Of course it will be larger, because the start index is still the same and the I has incremented by 1 or so. So this particular index which we find in any iteration related to any index I is of no use if it is kept in the map. It won't affect the result that we are trying to get from this particular logic. So the key which is present in this entry is of no use once we have gone through it. So any key in this map is useful only once. So we can remove all those keys which have been used. So let's first remove that key. So the key is removed. So by removing this particular key, we are effectively keeping the size of our map in check. It doesn't hold any information or any sum or index pair which is of no use in the future. This would effectively increase the running time of our solution. Now let's run this code for the sample test cases. Okay. Now let's run this. So it ran successfully. Now let's submit this. So it got submitted successfully. Let's discuss the time and space complexity of this problem. As we are iterating over the integer array, this is O of n complexity, and inside this we are finding out the entry which is less than or equals to the remaining sum. Now the complexity for floor entry is log of n. As we discussed, tree map stores the key in a binary tree fashion. So searching any value in a binary tree takes log of n time. The time complexity in this case is O of NlogN, and the space complexity, as we are storing only the sum for all the indexes, will go till O of n. Can we reduce the time complexity? Can we optimize this particular solution and bring the time complexity down to O of n? So now let's see how we can eliminate finding out the floor entry or the sum which is less than or equals to, so that we can find out the result in a much optimized way. So let's again go back to our sketchpad wherein we were discussing how we can approach further. So let's start from where we left off. So in the previous approach, we had two steps. We were storing the previous sum in the index, and in the second step, we were finding out the sum which is less than or equal to some value. So as we discussed that the step 2, which is finding out the sum which is less than or equal to some value, has a time complexity of log n, and we need to eliminate this particular line or this step so that we can bring down the complexity to O of n. Let's take a different approach here. let's plot the sum that we are getting from starting from 0th index to that particular index in a graph. So we put the index 0, which is minus 28, into the graph. We move to the second value, index 1, which is 53, and then we come across index 2, at which the sum is 33. Now if we find out sum between the index 0, which is the 0th index, and this current index, which is index 2, we get the sum as 61. Now 61 is still less than the target that we are trying to achieve, which is 89. So we leave this point. Now turn your attention toward these 2 points. The first point signifies index 1 with the sum 53, and the second point is index 2 with the sum 33. We find out the sum between the two. The sum will come out to be negative, and it will always come negative in this particular case, because the previous sum from this current sum, if it is greater, will always give sum as negative, and as we know from the constraint itself, the value of the target sum can never be negative. So this particular sum 53 is of no use to us. It won't give any answer to us, and we can remove it. Once we remove it, graph will look like this, wherein we have two values, which is minus 28 and the index 2 value, which is 33. We move ahead, we plot another value, which is index 3, sum 61. Now the sum between the two indexes is the difference between the sum at those two indexes, which is 61 minus of minus 28, which gives us 89, which is the target sum that we are trying to find. So we'll keep the answer with us, the window size, which is 3 minus 0, which gives us 3. Now let's focus our attention on the start index of this particular window. We discussed in the previous approach as well, if the start of a window has been found, it won't give us any further results, because any window starting from this particular index will be longer than what we have found before. So there is no use of this particular value. So from this point, all the points will be far, even if the sum is greater, and hence we can remove this particular value from our computation. Now only remains two values. One is index 2 with the sum 33, and other of the current index with the index 3 and sum as 61. We again find out the sum between the two, and we get it as 8. As it is less than the target, we do nothing and we move forward. We again come across a condition wherein the previous sum is greater and the current sum is higher than that. We see that the first value in our computation, the difference between the two is minus 1, which is less than the target. So we are not getting the required target. Now both the values are greater than the current value, and we know that if there exists a greater value than the current value, then it will always give us a negative result, and hence they can be removed. So we will now point by point remove the two values. We'll first remove the sum 61, and then we'll remove the next value, and at the end we'll only have a single point in the graph. As we have come to the end of the array, we cannot do any further computation, and the answer is 3 in this particular case, which is the same which we got with this previous approach as well. Now let's discuss the steps that we are doing over here. So over here we are doing operations on both the end of the values. If the current sum minus the sum at the start is greater than or equals to the target, we are removing the start. Now why we are removing the start? We are removing start because that particular index or the value at this start cannot give us any smaller window, similar to what we did in the previous approach. So we are removing that value. Now the third step that we are doing over here is, for the current sum, if it is less than the last value, then it will always give us a negative result, and do not need that particular index or the sum in our further computation, and we can remove that from the end. Now similar to previous approach, which particular data structure gives us these functionality wherein we can remove from both ends? So make a guess and comment down your guess below. But what concept that we are following over here is, we are doing nothing but monotonic sequence. So now let's see how we can code this particular approach. So let's now clear out the previous approach. Previously we were finding out the sum at each index and then putting that into the map, doing the logic in between to find out all the values which are less than or equals to this particular remaining sum. But over here we are not using any map, so the key value pair is not there. So we need to keep all this sum till that particular index starting from 0 in a separate array. So we'll first define that. Now we need to do the steps that we discussed. We need to find a data structure which can help us in doing the operations at both the ends. When I say ends, that means that we need something of a stack or queue. From both the ends, there is only a data structure which is dq, which is nothing but a doubly ended queue, which allow us to do the operations from both the ends. We'll putting the values from the end and then we'll be removing the values from both the end. In a singular queue, value works in first in first out fashion, but not in dq. That's the basic difference between the two. So let's define a dq which can hold an integer value. So over here we are using an implementation of dq which is array dq. There is another implementation which is linked list that can also be used. Now for every index we need to perform the operations that we discussed. We will be first performing the operations and at the end we need to add this particular index into the dq. Now why we are storing the index? Because from the index we can find out the sum starting from 0 till that particular index which is stored in this prefix array. So rather than using a key value pair, we are storing an index and then we are trying to find out the sum. We discussed that we will be using two steps. We will check if sum at index I minus sum at index at start of dq is greater than or equals to k. We remove the start index at dq. As we can find multiple values, we'll just keep on removing those start indexes. An empty check is very important and then we check out the value. We'll say if the sum at this particular index minus the sum at the first value is greater than or equals to the target sum. Peek first returns the value without removing it. Once we are sure that the difference between the sum at index I and the first value in the dq gives us the required result, we need to update the result with the window size and also remove the value from the dq. As the name suggests, poll first removes the value and return the value. Now the second step was performing an operation at the end of the queue. As we have not added the value, end of the queue lies the previous sum. If this particular sum is greater than the current sum, we need to remove the values. And similar to what we did with the first value, we need to continuously do that until we find out a value which is less than the current sum. So if sum at last in dq is greater than or equals to current sum, we remove the last value from dq. So let's write that. We'll check the prefix sum of the two. We peek the last index that is stored in dq, find out its sum if it is greater than or equals to the current. So we'll now remove the value from the last. Now let's run this code again in sample test cases. So it ran successfully. Let's submit this. So it got submitted successfully. Let's discuss the time and space complexity in this case. The time complexity in this case is O of n, as we're iterating over the array once here and then here as well. The space complexity is O of n, as we are using a prefix array to store the sum starting from 0 index to that particular index. So in this video we have learned a lot, starting from brute force approach to using a tree map and then to a dq. We have learned how to reduce the time complexity starting from n square to O of n log n to O of n. There are various data structures that we have used like tree map and dq, which will be very useful if you know about them in other problem as well. The logics and the intuition that we have developed in this problem will be useful in other problems. So I'll highly recommend you to go through step by step in this question with all the approaches thoroughly. Do let us know your thoughts in the comments below. And if you want us to make a video on any of the particular problem, you can comment that as well. Thanks for watching this video. See you in the next one.